Okay, today we are talking about CRISPR. And this isn't just some incremental new drug. This is a technology that gives us the power to literally rewrite the code of life itself. But, when you have the ability to edit our own evolution, that comes with a massive question. How do you stop that incredible power from spiraling completely out of control? And that really is the heart of the problem, isn't it? We've got this tool with, almost infinite potential for good, but also for irreversible, huge-scale harm. So how on earth do you build guardrails for a technology that can literally reshape the future of our species and our entire planet? Before we can even begin to talk about control, we have to get our heads around the sheer scale of what we're trying to control. The experts behind this framework have a term for it: unbounded amplification. It's this idea that a single, tiny genetic edit could spread uncontrollably with consequences that are permanent and, well, unimaginably far-reaching. Let's start with the big one: editing the human germline. We're not talking about changes to a single person here. These are heritable edits. They get passed down from generation to generation. The source material calls this lineage amplification without retroactive consent. Just think about that for a second. Future generations would inherit our edits without ever having a say in it. Then you've got gene drives. Now, these are engineered edits that are specifically designed to spread like wildfire through a wild population. Like editing mosquitoes to wipe out malaria. Sounds great, right? The problem is, once you let them out into the wild, there's basically no getting them back. We could accidentally trigger these massive, unpredictable ecological cascades that we just can't undo. And finally, there's the risk that hits a lot closer to home, the societal one. What happens if CRISPR is used not just to cure disease, but to enhance normal human traits? And what if only the super rich can afford it? Well, you could create a permanent, biologically enforced class divide. This isn't just regular inequality. The framework calls it permanent socioeconomic divergence. So you can see why this distinction is so important. Using CRISPR for therapy, to fix a terrible genetic disease, that's one thing. The risks there are mostly medical. But using it for enhancement, to augment traits that are already normal, that carries this much bigger risk of tearing society apart on a civilizational scale. Okay, so how do we even start to manage these massive risks? We can't just talk about them in abstract terms. We actually need a way to quantify them. And that's where this framework gets really interesting. It proposes a mathematical approach, a literal equation to model the very nature of biological risk. So here it is. It's called the core risk operator. Basically, the total risk, or omega, is the baseline biological state plus our intentional edit, or the bias. But then it's all multiplied by that absolutely crucial variable, alpha. That's the amplification multiplier. Alpha, right there, is the danger zone. It's the measure of how far and how fast an edit can spread. So let's connect this math back to the risks we were just talking about. For those germline edits that get passed down, that alpha value is transgenerational. It just keeps going through time, pretty much forever. The amplification is, for all intents and purposes, permanent. And for gene drives, well, alpha becomes ecological. It represents the edit's raw power to spread through an entire species across a whole ecosystem. So now its amplification isn't just through time, it's across space, and potentially the whole globe. And this is just brilliant. This perfectly illustrates that third risk. For genetic enhancements, alpha isn't even biological, it's socioeconomic. It becomes a multiplier for inequality, with the power to permanently split society. You see, the framework forces us to see all three of these things, time, ecology, and society, as just different flavors of dangerous, unbounded amplification. So, if the core problem is amplification, then the solution has to be about control, right? It's about putting the brakes on. And this framework proposes a system with 4 distinct levers, 4 control mechanisms, all designed specifically to get a handle on that dangerous alpha variable. Okay, the first lever is called time decay. I love this. Just think of it as a built-in expiration date for every single genetic edit. By default, the effect of an edit will fade over time, unless we, as a society, make a conscious collective decision to reinforce it. It basically forces every edit to be temporary, unless we choose otherwise. The second lever is quorum validation. This is basically a multi-key launch system, like in the movies. No single person, no company, no country can unilaterally decide to release a powerful edit. It requires independent sign-off from multiple genomic labs, biosecurity experts, and an international authority. Third, we have amplification stratification. This one's like a smart risk dial. The system is built to automatically dial down the amplification potential based on what kind of edit it is. It gets that not all edits are created equal, and it slams the brakes on the most dangerous ones by default. And you can see exactly how that dial works right here on this table. A somatic therapy that only affects one person? Sure, amplification is unrestricted. A germline therapy to fix a horrible disease? Okay, we'll moderate that a bit. But a potentially society-altering enhancement? Nope, that gets highly restricted. Its amplification is automatically dampened by 90% unless we can prove it's being distributed equitably. And the final lever, and maybe this is the most critical safety net of all, is the reversibility constraint. It's a simple, non-negotiable rule. You cannot release an edit into the world unless you have already built, tested, simulated, and publicly archived a working undo button for it, period. So when you put all of these pieces together, it's not just some static set of rules written down in a book. It's a dynamic system, one that's designed to learn and adapt over time. The whole framework is built to be constantly calibrated against real-world data to make sure our controls are always strong enough to handle our capabilities. And that right there is the key. As this quote from the source material says, this whole thing isn't about just guessing what might happen. It's about building a governance engine that's calibrated using hard data from past gene drive trials, from actually observing how these things spread in the real world. It's science-based governance for a science-based technology. And all of this entire framework, really boils down to this one elegant, powerful principle. True civilizational stability, it's just a ratio. It's achieved only when our layered control systems are stronger than the technology's inherent power to amplify. Our control has to be greater than the amplification. That's it. So this framework gives us the technical blueprint for control. We're designing the safety switches, we're building the dials and the undo buttons. The final question really isn't about the technology anymore, is it? It's about us. We are building the controls. But are we, as a global society, are we actually ready to use them?